Welcome to the series of lectures on nuclear chemical engineering. This is the first lecture wherein I will introduce what I plan to cover in the series of lectures. Let's first get started and define what exactly do we mean by nuclear chemical engineering. This is something that you wouldn't have heard as often as, let's say, nuclear physics or nuclear chemistry. So if you look at Wikipedia, there's an entry on nuclear physics, and it is defined in the following manner. Nuclear physics is the field of physics, which is obvious, that studies atomic nuclei. Okay. So, and its constituents, that is what is inside the nuclei. It doesn't take nucleus for granted. It tries to understand what is inside the atomic nuclei, and probably the interaction between its constituents, as well as interaction between different nuclei. Supposing when you are talking about nuclear fusion or nuclear fission, uh, we are interested in how different atomic nuclei interact with each other. In addition to that, there is the study of nuclear matter. What exactly do we mean by that? It may mean many things, but I will just give you an example. For example, you may have heard about neutron stars. Okay, so these are fairly exotic cosmological objects. So, and the properties of neutron stars are often part of nuclear physics. In contrast, or perhaps there are differences between nuclear physics and nuclear chemistry. Um, Nuclear chemistry, again going by a Wikipedia entry, is a subfield of chemistry, which is again obvious. And much of nuclear chemistry were fascinated, nuclear chemists were fascinated with radioactivity because um, chemists typically deal with chemical transformation. So radioactivity is about transmutation of um, one particular element to another. Um, but much of the behavior can be treated in the way chemists often treat chemistry. All right. So much of nuclear chemistry has to do with radioactivity. It is associated nuclear processes, um, and nuclear transmutation and nuclear properties. All right. So as opposed to nuclear physics and nuclear chemistry, there is no Wikipedia entry on nuclear chemical engineering. Okay. So in light of this, what do we do? Just to give you an idea on what is nuclear chemical engineering, you cannot really look up Wikipedia. So there is a definition of chemical engineering, which is probably whimsical, but it also tells you some aspect of this human vocation. Chemical engineering is what chemical engineers do. Like, so nuclear chemical engineering is what nuclear chemical engineers do, which might be a definition, but it's not a very helpful definition. So let's look at some other sources. Uh, there is this one textbook, which is a very famous textbook on nuclear chemical engineering. It goes by this title. It was written by two pioneers, Benedict and Pickford. The first edition of this textbook, was written in 1957. I think Benedict is from MIT and Pickford is from University of California at Berkeley. They wrote this book in 1957, and there was a second edition, which is co-authored by Levy in addition to Benedict and Pickford, that came out in 1981. So even that is fairly dated. It's more than 40 years since this book was published. As far as I know, there is no other book with this title or a title similar to this. So that gives you a set of contents which can be taught. And in fact, this course was taught in IIT Kanpur using this as a textbook. I would also be using some part of the material covered in this book. Let's understand, where do the nuclear chemical engineers typically come from. So the background of Benedict and Pickford um, is they had background in physical chemistry and engineering. So this is often um, a typical background of people who drift into chemical engineering. They have a mixture of physical chemistry. This is a branch of chemistry which is more quantitative and which has its own um, methods of studying chemistry. But the main point, or the main distinct feature of physical chemistry as opposed to organic chemistry, inorganic chemistry, biochemistry, and analytical chemistry, is that physical chemistry is much more quantitative. And nuclear engineering is about nuclear reactors and so on, right? So you have to appeal to um, other branches like heat transfer and so on, reactor design, to practice nuclear engineering. So they had a background which is a mixture of physical chemistry and nuclear engineering, and that is reflected in the contents of nuclear chemical engineering, this textbook, and also the methods that they utilize to unfold the contents in this textbook. Let's move on, and I will tell how I'm going to present this series of lectures. Uh, this is in a way typical of many adjectives in chemical engineering. For example, you can teach a course on electrochemical engineering, which is what I used to teach as an elective. So typically when you have some such course, you start with, let's say, thermodynamics of the system. Okay, so here the thermodynamics has to be slightly modified, because when you say thermodynamics, you are talking about, let's say, a continuum, a macroscopic material, and you're able to unfold its energetics. So here we may not have a macroscopic continuum, but still you can talk about energetics of nuclear reaction. Okay, so this we should be able to discuss quantitatively. That provides the foundation for uh, the material which we want to address. Then we talk about kinetics. Okay, so for example, again, just based on the analogy, if you're teaching a course on electrochemical engineering, you would have done electrochemical kinetics. Okay, because we're talking about uh, certain changes, the rates of change of something. So here we'll be talking about nuclear kinetics. Okay, so these can be measured and quantified, and you can write rate laws, which is very useful, right? So again, both these things are at a fairly macroscopic level without going into the constituents of nucleus and so on. We can discuss both these aspects. Then we typically talk about transport in nuclear systems. So this may be transport of many different aspects. For example, it can be neutron transport, or it can be certain aspects of radiation transport and heat transport. Okay, so again, this can be done fairly quantitatively. The underlying equations are well known. This will be dealt with following these two topics. And then there an important aspect of chemical engineering per se is that it has to do with separations. So typically in the context of nuclear chemical engineering, we'll be discussing aspects of separations that are involved in developing nuclear fuels. Okay, so nuclear fuels, let's say a certain form of uranium and thorium, these are never ever present in its pure form. It has to be, these nuclear fuels have to be extracted out. And sometimes after a fuel goes through a nuclear reactor, some aspects of separations has to be dealt with. So typically in chemical engineering, you either separate before sending the material to the reactor, or you separate after getting the material or the products of a products from the reactor. So separations, process separations is very important aspect. We'll also discuss that. Then it's engineering, so you have to discuss certain aspects of experimental methods that are typically utilized. It can be radiation detection and many other aspects we'll be dealing with. This is an ocean of methods available to you. We won't have time to discuss all the methods, of course. So we'll be addressing some parts to give you a feel for the experimental methods. It is also dependent on my own background in this area. So we will deal with some aspects of experiments. Then the central part again of any chemical engineering discussion, one aspect is separation, the other aspect is reactors. So we'll be discussing about design of nuclear reactors, process design, and so on. And one aspect which is very interesting in nuclear reactors is how do you control nuclear reactors? Okay, so this is very, very important from the point of safety and so on. So we'll also address this aspect. So control and design go together in nuclear reactors. So these are fairly traditional. In a way, this could have been taught in, let's say, from 60s or even from earlier days. Okay, so we could have dealt with all these topics in a fairly cohesive manner. But one topic which I would like to add, which is not there in probably in the textbook Nuclear Chemical Engineering of Benedict and Pickford, is a topic which we have been working for the last some years. Uh, this bit, uh, the formal foundation or the theoretical foundations are not very clear. This is often referred to as chemically or electrochemically activated nuclear reactions. So it is a bit controversial because the underlying mechanisms seems to be very different from the conventional nuclear fission or fusion. Not only that, so to have to develop accurate theoretical models, you have to have fairly reproducible experiments. Uh, so that is also a particular challenge in this field. Okay, so there are a lot of circumstantial evidence. There are many, many groups which have done experiments in this area, including ours. However, these experiments are not very accurately reproducible. Okay, so the reason for this is deep. We will go into these reasons. So this is also the this addressing this particular topic is has certain utility in from the point of how scientific disciplines develop. Okay, so this we will try to deal with some aspects of history of this field and why it making developing models for this system has been challenging. We'll address all these issues. So what we will do is, in addition to all these topics, this topic will also be addressed in this course. This summer, this topic will be addressed by Professor K.P. Rajiv from the physics department. He's an experimental condensed matter physicist. He's also been my collaborator in this field for the last more than 5 years. We've been working in this area for more than 5 years now. So this aspect will be primarily dealt by Professor K.P. Rajiv this summer, but I'll be dealing with these topics. But perhaps in the future, I will also record some more lectures once Rajiv and I agree on what can be taught here. Let's move on. The textbook we would like to use is not Benedict and Pickford, for this particular reason why I chose this particular textbook. So when somebody takes this course, when some student takes this course, I want the student to get an understanding of the status of nuclear engineering in India. For example, if you go to ask the question, what kind of nuclear reactors are typically used in India, what kind of nuclear fuels India is trying to use, and so on, we have to have a particular source that also discusses the status of Indian systems. So I always say that science is perhaps universal, engineering is often local, right? So the approach to engineering, the economics of engineering is fairly local. So I want you to get a good idea of nuclear systems available in India. So there's this very good book by scientists from, I think, Baba Atomic Research Center. This is the book we will use. In addition, this book is freely available. Okay, so there is this Indian Association of Nuclear Chemists and Allied Sciences. They've been very kind enough to post this book for as you can download it for free. So you should make use of this opportunity to use this textbook. It's a very clearly written book, and this is the book we will be using predominantly for this course. Of course, there will be additional references which I will mention as we progress along the course. Okay, this is the first time I'm teaching this course, so we will improvise as we move along. So in the next lecture, I would provide some historical perspective, especially from the point of measurements, on how we went from high voltages, vacuum, and X-rays to nucleation of nuclear science. That will be the topic for the next lecture. Thank you.